So we return after the break. And this next session is going to be great. It's going to be about glaucoma. It's a very interesting field that's going to explode, I think, because of imaging. It's going to be a new era coming up, I think, for glaucoma. And one of the persons leading that charge is Don Hood, and he's going to be talking to us about diagnosing and understanding glaucomatous damage based on a single swept source OCT wide field scan. Don.
Thank you, Rick. So first let me say that we're going to modify the procedure a little bit here. We had some extra time as it was. We are missing a speaker at the end of the program, so that what we're going to do is take the 6 papers that were supposed to be in my session and Dr. Liebman's session and combine them. And we'll have 2 papers, discussion, 2 papers, discussion, 2 papers, discussion, and then there should be plenty of time even for discussion after that. Okay, so first the obligatory financial disclosure. So I want to tell you about a 1-page report that we've designed with Topcon to help clinicians quickly diagnose and also understand the nature of glaucomatous damage. And it's based on a single wide field swept source cube scan. So first, a few background information. So glaucoma kills retinal ganglion cells and their axons. So this is actually a scan of my eye. If I had glaucoma, the layers that would be affected would be the ganglion cell placenta plexiform layer and the retinal nerve fiber layer. Actually, I should point over there because that's where the face is pointing at, but it's kind of hard to do that. This would be an example of a ganglion cell, and then its axon is traveling and making up the optic nerve. The most common, historically, the most common scan that the glaucoma specialist looked at was a circle scan around the disc, and this is what it looks like here. And again, this is the retinal nerve fiber layer that's affected by glaucoma. Okay, now, as most of you probably know, there's no litmus test, no gold standard for detecting glaucoma. It's defined as a progressive optic neuropathy, and most glaucoma specialists are looking for both anatomical and behavioral changes. So for anatomy, you've got the fundus exam augmented with photos. Now you've got the OCT, and for behavior, you have the visual field, usually a 24-2 or 30-2. All right, so the report I'm going to tell you about is based upon a lab report that we developed and published about in BJO, and that report actually required 3 scans. We had a scan of the disc so that we could look at what's retinal nerve fiber layer there. We had a scan of the macula, and then we had a circle scan. And the criticism was, oh, that's too many scans, right? And from that, we produced this report. All right, now, because the swept source is so fast, we can now do all that with a single scan. And the scan we use is 9 by 12 millimeters, so it's a wide field scan available in the Triton and Maestro. So 9 millimeters by 12. This would be, it's got 256 B scans. Here's the B scan through the fovea, and that would be the ganglion cell placenta plexiform layer, and that's the retinal nerve fiber layer. And this has pretty good resolution because it's got 512A scans. From that, we're going to produce this report. All right, so this, first of all, this here is the circle scan. Well, how did we get a circle scan? Well, it's actually derived. So we take the retinal nerve fiber layer thickness, so the software takes the retinal nerve fiber layer thickness, and it takes a circle region here, actually an annulus, and then averages the OCT information and produces a derived circle scan. So it would be the equivalent of that. All right, so this is more, I want to emphasize that this is more than just a report. It's actually a method or a process that's based on 5 principles. So I'm going to introduce the report at the same time I tell you about the principles. So the first principle is that the circumpapillary scan image should be large enough to see details. So often in most machines, this image, if it appears at all, appears like that on the glaucoma reports. Not much use, at least to me. So you want that to be large enough so you can see if there's segmentation errors, so you can see if it's a poor scan, you can see where the blood vessels are, and if you blow it up, you can see in this case, there's almost no tissue left there. That's where the damage is. All right, the second principle. You have to understand the relationship between regions of the circumpapillary thickness, that is, regions of this thickness plot, which is the distance between these green lines, and regions of the retina. All right, so to do that, we developed a map that related the location that the axons from the ganglion cells enter the disc to where the ganglion cells are. So we have a map from here to here. And we made use of, this is sort of a schematic map, meaning it's on average, it's for teaching purposes. So the dark circle here is the disc. That's where your circle scan would be. So let's just take the point here that's about 12 o'clock, and the point here that's about 6 o'clock. And this region in here, which is plus or minus 15 degrees, plus what would be called a nasal step on a visual field, that region has a unique relationship with the temporal half of the disc in the sense that all the axons entering the temporal half come from here, and all the ganglion cells in this region send their axons there. Okay, that traditionally has been plotted as what's called a T-Snip plot. It's been plotted based on the early scans that started the circle here. So most of the machines until recently had this as a T-Snip plot, meaning it went from temporal to superior and so on. What that does is split this in half. So the inferior retina is over here, the superior is over there, and even some of the superior is over here. Crazy. Instead, what we're advocating as part of principle number 2 is to get a real spatial sense of what glaucoma is doing. You want to plot it as an end-stin. Now, what does that mean? Right? Doesn't roll off your tongue, but end-stin plot. That means you want to plot it as if the scan started here and went counterclockwise, because now the central part of your visual field and the central part of your retina is in the center of your thickness plot. We've done a lot of work on the macula, and let me define what we mean by macula, because different specialists use it different ways. By macula, I'm going to mean plus or minus 8 degrees from fixation. It's the region with the highest density of ganglion cells. It represents less than 2% of the retina, but over 30% of the ganglion cells. It's the region you need for reading, driving, and accurate face recognition, let's say. We know now that this is, on average, where the macula is. So it's not simply in the temporal region, it overlaps the inferior region as well. All right, so let's take a look. So this is now an end-stin plot. So if we blow this up, you can see it tells you where to look if you're looking for damage within 15 degrees or so, plus a nasal step, and it tells you where your macula is. Okay, so let's look at the other pieces of the report. This is the retinal nerve fiber layer thickness. It's pseudo-color. So if we take a line through here, what we're actually doing is looking at the thickness of this right here. All right. Dark red is thick. Dark blue is thin. Right? Now, if you only look at this, right, you're going to miss some macular damage. So one of the things we're very strong on is you want to look at the ganglion cells in the macula as well. All right. So you want to look at the macula as well. So we have a ganglion cell plus in a plexiform layer thickness map of the macula. And so now we're looking at this layer. And we're going to look at this much of the scan, and that's what's over here. And again, this is the thickness map. Dark red is thick. Dark blue is thin. That's your foveal center, but you also see there's something going on here. All right, number 4. It's often easier to see damage if you have probability maps as opposed to thickness maps. So we're going to take this thickness map. Here it is. That's the thickness map. Remember, that's thick. That's thin. That's superior retina. And we're going to turn it into a probability map in field view. What does that mean? Well, first of all, Point by point, the software compares the thickness here to a group of normals, adjusted for age, and then plots the probability. So, and we flip it along the horizontal meridian to make up for the fact that as you look at me, I'm standing on my head in the back of your eye, right? So the image is inverted. Right? Dark red here is significant at the 0.1%. Red would be 1%. Yellow would be 5%. It's a continuous probability plot. And green would be 10% within normal limits. All right? So this defect here is that defect there. Okay, we do the same thing for the retinal nerve fiber layer. So we take this thickness map, turn it into a probability map, thick, thin, superior retina, and this probability map here is flipped. So this is the inferior retina now, and this shows you where the significant thinning is. 0.1% within normal limits. All right, with only this report, we can answer the following questions. Is optic neuropathy present? And where is the damage? Does it include the macula, for example? So in this case here, here's your macula. This is dipping down here. That you've got damage close to fixation, which may or may not appear on your 24-2. There it is. You can see it there. It's in the macula. There it is here with this missing, right there. There it is on the probability map in field view, right? And there it is on your thickness map. And there it is on this probability map. And then here's the same thing for this damage over here. All right, so I want to relate this to what I'm going to call the most common clinical paradigm. So if you go around the world, the most typical tests that you'll find the glaucoma specialist using is an exam of the fundus of the disc, often accompanied by photos, a 24 or 30-2 visual field that has spacings of 6 degrees, and then an OCT disc scan. And clinicians, especially for the OCT, tend to depend upon these quadrant metrics and this metric here. We don't use metrics at all. And many look at this as they should. All right, so I'm going to give you an example for clinical utility. This is an example I've used in a number of lectures with glaucoma specialists. And I'm going to show them the tests they usually have and ask them whether this eye has glaucomatous damage. Probably, definitely doesn't, or I'm not sure. Here's the fundus photo. The experts in the room, some may call it normal, some may see something that's a little suspicious. Here's a visual field. If you use metrics that are typically used, normal limits, these were the Oates criteria, right? If you look at this, however, that might worry you. Even this should worry you. Here's the OCT. All of these metrics are green. They look good, right? So that looks normal, right? All right, so when I asked glaucoma specialists to vote, in this one group, 40% said it had glaucoma. 60% was in this group here, right? Most of them in these two. All right, here's the report. What do you think? I'm going to argue, if I've been clear enough in what I'm describing, you can quickly see that there's damage here. So I showed them this for a couple of seconds, and then I went back, and now 80% thought it had glaucoma, right? And 20% only in this group. Now, why 20% in this group? Well, that's a little surprising to me, but you get skeptics, right? So why do I say quickly a glaucoma? Well, the first thing, I know there's a lot of macular damage that's being missed. The first thing I look is here. I mean, that's classic early glaucomatous damage near fixation. There it is on the probability map. It doesn't quite make it into the red here. That's why it didn't show up on the statistics, right? And then there's something going on up here, but that corresponds to this and actually here. So this whole area is actually affected. All right, so why 20%? Well, that gets me to the last principle, and that is you can confirm damage by topographically comparing OCT with visual field probability maps. So here's the 24-2. This indicates abnormal regions. If you just look at the upper visual field for now, we put that there. That sort of looks like it matches. Here's the 10-2 that I'm worried about. If you circle this and circle the 10-2 points, I guess I should have, I'm sorry, I should have made it clear. On this map here and here, the big points are the physical locations of the 24-2, and the little points are the locations of the 10-2. So when I'm circling these here, I'm circling the corresponding points on here. All right, quickly in terms of validation, here's a study in which we had had more than 102 eyes. We wound up with 102 eyes that had early glaucoma. Early glaucoma defined based on mean deviation better than -6, or they were suspects. So they all had funky or abnormal looking discs. As a reference standard, two glaucoma specialists, the next speaker, Dr. Liebman, was one of them. Both specialists were not involved in these patients' cares. They were given everything we had. They had OCT, they had disc photos, they had 24-2, 10-2, and so on. They agreed on 102 eyes, 57 with glaucoma, 45 healthy suspects. I had only this report. I had no other information. I didn't have fields. I didn't have photos. I made 2 mistakes using this reference standard as the ground truth, right? And much better than any metric. So the metrics, meaning the quadrant thickness or the average thickness or the mean deviation of the field or pattern standard deviation, none of them did better than 13 mistakes. Now the point here is not look at me, how good I am. The point here is look at how much information is in here, because that's all I used. So if that information is there, we were optimistic we could start using artificial intelligence instead of metrics if you wanted to have a simple way to deal with this. And we've only started this work, but the first study we published was a proof of concept. We used an artificial intelligence program that was stock. It was right off the rack, and it made only 7 mistakes. Most of them had to do with blood vessel location. So we think we know how we can improve this. And in fact, it wound up only using this information. So we think we can do a lot better if we use all the information. And that's the one-page report. Thank you.